formations. And what can computer modeling contribute to this? We can here also contribute to comprehension, to the vicious circle of cardiomyopathy and infarction, because they, as they go on, they make things worse and worse, and this can be better understood. And we can uncover hidden properties. For example, we can measure strain in the heart with the magnetic resonance tomography, for example, but we cannot measure stress in the heart. And using computational modeling, we can uncover the stress in the heart from measurements of strain. Also, personalization of diagnosis and therapy planning is in the scope. We can make a prognosis of cardiomyopathy or a prognosis of infarction, whether this patient is likely to move into heart failure, or whether this patient will survive the infarction and feel happy until the end of his or her life. Also here we can focus on the planning of pacemaker, positioning of the electrodes. We can also look into surgery planning. And we heard a talk in this workshop by Seiryo Sugiura, the first talk, where the surgery planning of congenital malformations was in the focus. Also here we can make the optimization of medical devices. Pacemaker electrodes, catheters for electrophysiology can use elastomechanics to move on and make the devices better. Next block was the fluid dynamics. Frequent diseases is clot formation during AFib, a wrong flow and clot formation in ischemia and infarction and in cardiomyopathy, valve defects. What is often investigated also, many publications about fluid dynamics in stenosis in arteries and aneurysms, but this is not focused so much on the heart itself, so I will not comment on that. And we have seen an excellent talk here about clot formation and during AFib, or clot in the ventricles in that case, by Rajat Mittal yesterday. And so now here is also important aspect, the comprehension of pathomechanisms, the comprehension of clot formation, comprehension of valve defects and their consequences, uncover hidden parameters from the measured data, find diagnostic relevant other properties. We can contribute to personalized diagnosis, the quantification and prognosis of regurgitation, the quantification and prognosis of stenosis in the valves is a very important aspect. And we can contribute to personalized valve reconstruction or valve replacement. And we have heard about this in a talk by Francesco Migliavaccia, and also Ivan Fumagalli had a talk here in this workshop on the image-based personalization of these models of the valves. We can contribute to the optimization of medical devices. Obviously, we can contribute to artificial valve design. We can support the development of the next generation of TAVI. And also here we heard an excellent talk about that. And we also can contribute to artificial heart and cardiac assist devices. And now the fourth block in my scheme in the beginning is the circulation. And we have to understand that the heart here, the left ventricle, pumps into a systemic circuit, and the blood comes back to the right atrium, goes from the right atrium to the right ventricle, and is pumped into the pulmonary circuit, goes to the left atrium and back to the right ventricle. And we have seen some talks where they took, the authors took into account that there is a preload and an afterload of the ventricle that we have to take into account. We are meanwhile convinced that it is important to make sure that you have a model included of the whole closed loop, because in the beginning with our elastomechanics simulations, we came up with a situation where the stroke volume of the right atrium was continuously different than the stroke volume of the left ventricle. And this is obviously unphysiological. This cannot be true. So you have to close the loop. You have to make a 4-chamber investigation, and you have to make a closed loop of the circulation. Otherwise, it might be that your simulations are not realistic. There are also diseases. Hypertension is mainly perhaps a point where we cannot contribute so much, but always if you talk about right-sided heart failure, or if you talk about diastolic heart failure, then it is extremely important to look at the whole closed loop. Here I showed the picture again, and here I'm comment a bit more on the coupling. And the coupling that is often taken into account, that is more or less trivial, is that the calcium release in the myocardium cell leads to tension. And what also the calcium binding to troponin and tropomyosin will change the calcium concentration in the cells, so there is some action back. And then we have stretch-activated channels, and the conductivity tensor, the electrical conductivity tensor will change with deformation. Here in this area, we have the computation of fluid dynamics with moving boundaries. That's the first step, that you just take into account that, for example, the left ventricle is changing the geometry continuously, and you have to make computation of fluid dynamics in time-changing boundaries. But in the other direction, you should also take into account the dynamic pressure that comes up from the fluid, and that works also on the endocardial wall. And so we have a quite complicated fluid structure interaction, and we have the valve dynamics that we have to take into account here. And here with the circulation, I talked already about the preload and the afterload, which we think is very important, and we have to take into account. And here I give an example about the baroreceptors. The baroreceptors in the aortic, in the arc, they give signals to the sinus node, and we have here some control circuits that might be important, and we should perhaps take into account. This is a slide where I look a bit more into these control circuits. Here on the first column, we have the depolarization and repolarization, the electrophysiology that we talked about. Here we have contraction and relaxation, the elastomechanics that we talked about. And here we have the pressure and the flow, the fluid dynamics that we talked about. We talked about the peripheral resistance that is changing. And now here I included another line, that's the medulla oblongata. And this is sending out signals into the vagal and sympathetical system to change the heart rate via the chronotropy. They can change the delay in the AV node via the dromotropy, and they can change the contraction, the tension development in the ventricles via the inotropy. And here we have a mechanoelectric feedback that we already talked about, and that is included in some of the models. But here we have the Frank-Starling control, which is very often omitted. Here we have a control with chemoreceptors, so we have to take into account that the peripheral load is changing continuously. So if you climb upstairs, immediately the peripheral load will change. So we have a changing peripheral resistance. And here we have the sympathetic and the vagal control, which we normally do not include into our computer modeling. And to bring it into one single sentence, most of our, I think all of our computer models of the heart, they don't show any heart rate variability. But in particular in Milano, there is a strong group working day and night on heart rate variability, and this doesn't show up at all in our computer models. So maybe we have still something to do there. Now I've summarized this. I think the prerequisite for good modeling of a diseased heart is that we have we want to do something for the patients, for the cardiologists. So we have to have a good model of the diseased heart. And if you trace back to these things that I mentioned, arrhythmias, cardiomyopathy, ischemia, etc., then we see that in the diseased heart, we have a changed geometry. Sometimes the heart is dilated, sometimes the wall is thicker, sometimes the valves do not open or they open it at the wrong time. Sometimes we have malformations. Then also the structure of the tissue will change. We have changes in the fiber direction. We can have scar tissue in ischemic hearts. We can have fibrotic tissue in hearts of patients with AFib. We have a stiffening in hearts with the cardiomyopathy. And then we have also changes in the function. The cell models change if the heart is an ongoing arrhythmia. We have ectopic centers. We have conduction velocity changes. We have reduced tension development. And so I say sometimes say we are quite good in modeling the healthy heart, but that doesn't bring any profit for a patient. We have to concentrate much more on modeling the diseased heart. And I will show you in the next slide that this is sometimes not so easy. So we are only halfway through if we model the healthy heart. So the first example I'd like to give here is the modeling of a fibrotic atrial tissue. And here I refer to a work of Jorge Sanchez from my group. He had the job to make the best computer model of fibrotic tissue. And so he came up with this model. So we have here a piece of tissue, and we have collagen in this tissue. We have fibroblasts with their action potential, and we have myocytes. And these myocytes are changed, for example, in an AFib heart due to a persistent afibrillation. We have some remodeling. We have this TGF factor, the transforming growth factor of the beta family that is changing these the action potential of these myocytes. And we have a coupling between the myofibroblasts and the myocytes. And we also know a little bit about this coupling and can include that into the models. And so Jorge made a very detailed model in the micrometer scale. You see here a mild fibrosis, and here is severe fibrosis in a histological cut. And this is the in silico model that he made out of it. And you see that there is an average length of fibrotic tissue here of 100 micrometer. And to make sure that the computer model of electrophysiology is good, you need an extremely large number of voxels. And here is now the calculation of the spread of the depolarization front, which is initialized here. And you see how the front is moving through the tissue, and the front is then moving beneath such a catheter, which is the HD grid catheter of Abbott, which you can buy currently, which is very popular. And what you see here in color code is the extracellular potential. So this spread of the depolarization front is calculated with millions of cell models, including all these things that I just mentioned. And then the extracellular potential is calculated, and the signal that you can pick up with these electrodes is calculated. This is, by the way, all done with OpenCarb. And you may have heard that we, from Karlsruhe, joined the group that is pushing OpenCarb into open source. So you can download the first parts and a large option. You have many, many options to use OpenCarb to do these calculations. And here is now the electrogram that Jorge calculated. Here he only included some cellular heterogeneity. Here he included only collagen. And here he had the full model where you switch on heterogeneity and collagen. and then you get a bipolar electrogram that looks like this if you measure the bipolar electrogram between these two electrodes. And if you compare now with the clinical electrogram, the typical clinical electrogram of a bipolar signal above fibrotic tissue, you see that we are not really there, but nearly there with our signals. So it might be that our computer model of the fibrotic tissue is already very near to reality. The modeling of ECGs for better annotation using machine learning is the next topic of my talk. And I will only show you one slide about atrial flutter. It's part of the myATria project, and it has been published in the Transactions on Biomedical Engineering lately. So the Giorgio here made 1,265 simulations of different classes of atrial flutter. He always calculated the ECG, and then he was able to train a machine learning machine and find the type of atrial flutter from the ECG with a quite nice accuracy, I would say. I would spend a bit more, some minutes more on the modeling of ECGs for the localization of ectopic foci. Can we directly localize the ectopic foci without the reconstruction of the source distribution, without patient-specific models, just using machine learning? That was our question. And so we set up a database. We set up a database, and we used the MRI data or the publication here from the 1,093 healthy subjects, and they made a shape model of the ventricles so that we could create many different shapes of the heart. Then we shift and rotate the heart inside the body, and then we place 300 ectopic foci on the heart, and then we calculate the ECG that comes out of that. And so with 1,000 shape variations, 3 positions, and 300 ectopic foci, we end up with 900,000 body surface potential maps. And in the next generation, we will have also AP and endocardial positions, and we end up with 1.8 million simulations. And with this, we feed a machine learning machine. And this is one example with a right ventricular epicardial focus and the right ventricular endocardial focus. And you see the spread of depolarization on the heart, the body surface potential maps, and here a visualization that includes the heart and the body surface potential map. These are just 2 examples out of these 900,000. Then we feed these into a normalized body surface potential maps. And here you see 4 different body surface potential maps as a function of time. And these are used to train the machine. It's a convolutional neural network classification and classification regression type thing. So in the end, we create a probability map where the focus is most likely to be. And here are the error bars, and I have to translate that from the percentage into millimeter. In the rotational coordinate, we have about 4 to 5 millimeter uncertainty, and in the apicobasal coordinate, we have about 3 millimeter error to localize an ectopic foci. And I say again, without any computer model of the body, without any inverse problem algorithm that takes into account lead field matrix, etc. And this is very amazing, and we think it's very important. Next, I will comment a little bit on cardiomyopathy. The dilated cardiomyopathy is a disease where the left ventricle becomes larger and thinner. And this was a collaboration with a group of Beatriz Trenor in Valencia, and Albert Dassi did this together with Tobias Gerach. They went very much into literature, and they found that the fiber directions are changed in dilative cardiomyopathy, from 60 degree, which would be healthy, to plus minus 30 degree, or things in between. Then we found out in the literature that the elastic properties are changing and the tissue becomes more and more stiff. And so we used the Guccione model, and we changed the factor C here and scaled it several times to make a good model of the DCM passive tissue properties. And then we did a cellular remodeling based on the latest versions of O'Hara and changes of formulations of sodium and other currents that have been published in the past. And for the coupling of the electrophysiology to the elastomechanics, we used the Land model for Land and Steve Niederer, who will be the next here to give his talk. They created this model. And we also included the circulatory system, and we also changed a little bit the peripheral resistance, peripheral capacitance, etc. And so we came up with a very complete coupled model of electrophysiology of the dilated cardiomyopathy. We have a changed cell model. We have the Sander-Land model here for the coupling of electrophysiology to the elastomechanics, and we have changes in this circulation. We have a four-chamber model of the heart, and then we can investigate what happens if we just change one of the parameters alone, or what happens if we change them all together. And this is something interesting. It improves the comprehension and understanding, and it might also lead to a better diagnosis, because it might be possible to see whether basically the passive properties are changed, or whether more the contractility and the tension development is changed. And so we see here how this, in the dilated control case, the pressure volume loop is changing if you increase just the stiffness or just other parts. And this, we think, is very interesting. On Monday, we had a talk from Ekaterina Kovacheva, who is in my group, on modeling hypertrophic cardiomyopathy. And so I will not go into the details. Here is the healthy case of this, and then she made a couple of changes that are also motivated by the literature, and so we come up in the end with also a model of the hypertrophic cardiomyopathy, and we can see what happens if we increase the stiffness or if we decrease the tension development, and we can see here the velocities of the nodes in the heart. This can be measured with MR imaging, and so it might be possible to use an MRI image and get more information about stiffness and tension development from these data. In the very last minutes of my talk, I want to very briefly comment on modeling valve defects. This is very new in my lab, and we are not leading worldwide, let's say. We are lagging a little bit behind, but we are also working on the fluid dynamics modeling, and this is a computer model of the mitral valve regurgitation. We use computational fluid dynamics. We use the software package OpenFoam, and there the Pimple algorithm. We take a Newtonian fluid, viscoelastic fluid, laminar flow. We include the large vessels in the in and outflow tract, and we use our dynamically contracting left ventricle, which you have seen from our elastomechanical modeling. And the valves are modeled with a dynamic porosity model. And you have seen similar approaches like that in other talks, where, of course, the modeling the valve as with a dynamic porosity model is not as precise as in reality, but it makes calculation time much faster. And then we also here used investigate different variants of mitral valve regurgitation. So the size of the hole and the location can be changed. and the porosity of the valve is switched. This is the porosity of the aortic valve, and this is porosity of the mitral valve. And these curves are motivated by the standard change of volume per time, so that these curves are replicated by our model of the valves. And this is just one example where you see the jet here, and in different visualizations, you see the jet that goes back from the left ventricle to the left atrium, and we can now play around with the severeness of the disease and with the location, and try to get more information out of that. So this is my last picture, and I would suggest that we in this community should discuss some aspects a little bit better as compared to what we did in the past. Do we really understand the interplay of fibrosis that we measure with late enhancement MRI and the electrophysiological properties? Electrophysiological properties are low voltage and slow conduction. Can we translate the contrast from late enhancement into electrophysiological properties? I would say no, we cannot do that yet. We don't know, don't know enough about it. Do our models already reproduce all pathological signals of the heart, imaging, electrograms? And you have seen an example how we still struggle with producing simulated electrograms that resemble the fibrotic, the electrograms that you measure above fibrotic tissue. My comment on CRT optimization, cardiac resynchronization therapy. I fear that we do not really understand the pathology of the electromechanical coupling of during heart failure. So there's again another point where the heart in heart failure has to be described a slightly different way as compared to what we did, what you do today. My comment on modeling elastomechanics: most often a 4-chamber model plus circulation is essential. I see so many simulations where I only see the left ventricle with no preload and no afterload. I would say this is very dangerous. Still, there's no link between modeling the controlled circuits of the heart and our computer modeling of the heart. Our hearts do not show any heart rate variability, and there's also some room for improvement. And with this, I would like to say thank you very much, and I'm open for the discussion.
Thank you very much, Professor DOESSEL, for the very comprehensive overview and lecture about the interplay about the heart models. Please, there is a question from Alfio Quarteroni.
Olaf, thank you very much for this very inspiring talk and for the list of questions to be addressed at the very end. This is a roadmap for many, I guess, many young and less young people. I have one specific question, and this is about your, say, integrated model where you account for baroreceptors from one side, for heart rate variation from the other side, for the sympathetic nervous system, and so on and so forth. Do you have a way to account for different time steps or different characteristic times that enter into play when you consider such a broad map? Thank you.
Yeah, thank you for the question, but I fear that I have been misunderstood. We do not have this model yet. So I think this should be something that we all should look at. And of course, you're right. The heart rate variability can only be measured if you take at least 100 heartbeats in a row. And our computer models will have, need a lot of time to make 100 heartbeats in a row. So we would have to have other means to take this into account. And I don't know yet how we could do that.
Thank you very much.
There is a question on the chat. I'm about to read the question. So first of all, a question from Elias Carabelas. Thank you for the great talk. concerning the valve models, did you do any sensitivity analysis with respect to the regurgitation position in the hole in the valve?
Yes, in fact we did, but these are very preliminary results. And we looked, for example, at the regurgitation volume, because this is something that is, well, bad for the patient. If the volume that goes back from the ventricle to the atria is too large, it becomes dangerous. And the volume that goes back into the atria, it seems as if it does not depend on the position. It depends strongly on the orifice, and our curves resemble those that are known from literature, from the effective orifice diameter and the volume. So that fits quite nicely. And we until now would say the position of the orifice in the valve is not so important.
There is another question, raised hand by Professor Trajanova. So please, Natalia, the floor is yours.
Hi, hi Olaf. I really enjoyed your talk. Thank you very much for this sort of very broad overview. I wanted to focus on your part where you discuss modeling of fibrosis. You're representing fibrosis by coupling of fibroblasts and myocytes. I was wondering, why did you guys make this choice? There is no evidence that in intact tissue there is connection between fibroblasts and myocytes electrically. This has been done only in Petri dish, and despite years of searching for functional connection between myocytes and fibroblasts in vivo, there is no evidence of that. So it is possible that, you know, fibrosis might need to be modeled differently. There have been numerous ways of modeling it. We incorporate changes in the tissue, in the myocytes that are in the fibrotic regions. There is the whole way, the percolation way that Ed Wigman has pioneered. Yes. But the coupling specifically is not something that exists experimentally.
Okay, I would say all the other aspects that you just mentioned are also included. So all what we know about electrical remodeling is included, and the percolation that Ed Wigman introduced first is also included, because you have seen these little patches of collagen. And well, I think the idea of the coupling of the fibroblasts and the myocytes comes from Peter Kohl, who is now in Freiburg, very nearby. And so that's maybe the reason why we have implemented it.
No, it's been only one study in the sinus node. There is no intact cardiac tissue, and that has been a debate for many, many, many years. And there is really...
I have different information about that. Yeah. I have heard about more publications that also claim that at least there are gap junctions between the fibroblasts, myofibroblasts.
It has not been proven that they are functional so far.
Okay, but then I would more or less say it's an open question. Let's follow that. I will focus more on that. I accept your hint, and I will look into that. But at the moment, I'm not convinced that this is already solved.
The reason I'm saying is that it used to be that we did it that way for a long time, and every time that I would write a paper with that, we will get a lot of criticism because of the really inhuman. You know, it is possible that in other species there may be, but nobody has ever demonstrated that it exists in the human. In intact tissue. Yeah. Anyways, this was just my personal struggle, so I wanted to relate it as well. Thank you, Olaf.
So now there is a question by Professor Wigman. Please, Professor Wigman.
Right. Thanks. Yeah, nice overview, Olaf. I appreciate all the efforts. So my question is about going to these huge models with all these mechanisms. How can we ever hope to validate them? There are probably tens of thousand parameters, let alone spatial heterogeneity. How much are we going to be able to trust this, or when will we be able to trust these models?
Yeah. So I would say, maybe I forgot this. I think I forgot this message in the end, that if we talk about the a digital twin, I think this is not really what we are aiming at. We are aiming at a model, a computational model that is solving just a very specific problem of the cardiologists. And if you want to have a model that is good for AFib, it's not a good model that is good for cardiomyopathy. So there will be different models and with a different focus. And I think that we will, whenever possible, we will still go into just a model of the electrophysiology and take the elastomechanics as some boundary conditions. And you can go through all the others. So whenever it's possible, you would just solve one of these, the elastomechanic problem on its own, and do the rest in form of boundary conditions. And if you then in the end can predict, that's the question about the evaluation. My claim is that you have to predict something, some measurements that you did not feed into your model. And if you then are able to predict some measurements that are not included into the model properly, then you have a good model. There are others that are more from the clinical point of view. They say we just use the model and look into the patient output. I'm not so happy about that. If we just look whether the patient feels better or worse, I would feel much more comfortable if you validate our computer models by reproducing measurements that have not been used by setting up the model.
Okay, thanks.
Please, one last question I would suggest from Professor Planck.
Hi, Olaf. Very nice talk. I have one specific question for you regarding, so we are not happy the way you replicated the extracellular electrograms in your fibrotic model. As we have done, as I've done a lot of microscopic electrogram modeling and measurements during my PhD thesis. So here's my take on it. I think this depends. You won't be able to replicate that one by one under those circumstances. A couple of things that play a role here is what is the size of the electrode, what is the spatial scale of the electrode, what is the spatial pattern you are using to model your fibrosis. These two things matter. What I can figure out is what are the average delays, because you're gonna create a zigzag pattern in your tissue, and you get an idea of what delays is between different wavelets. But I don't think it will be possible in the foreseeable future to really map this one-to-one in a computational model. This is too down.
Yes, I fully agree, but there are important characteristics of the signal, and I think we should reproduce the most important characteristics. There are some characteristics that are very easy to understand, and they are measured sometimes. That's the zero crossings per time. There are others that are more intelligent, like the entropy, and we also look into the recurrence plots, for example. And there are measures that describe this signal properly, and we should reproduce with our model a signal where these general features are reproduced as well. Yeah. And with the size of the electrodes, you're absolutely right. And Deborah Nairn in my group has a PhD in particular on that topic. She will show her results on computing and cardiology in 2 weeks from now, where we very thoroughly investigated the size of the electrode, because this is a full bidomain model, and the metal object is included into the simulation.
Okay.
So thank you very much, Professor DOESSEL, for the very interesting contribution and for the discussion. For the sake of let's say, respecting the schedule, I would suggest to, let's say, stop the questions and postpone the question for the coffee time. Just remind that for those who would like to interact with Professor DOESSEL, the room, the virtual room is room D. So
Yes.
thank you again. And I would, let's say, move on with the next plenary lecture.
I guess I have to step out, and I don't know how to do that. Stop this. Yes. Now I'm.
Also, you don't have to do anything.
Yes.
You can stay there.
Yes. Thank you.
Thank you.